Okay, class, this is Chapter 19, Section 1, Oxidation and Reduction. I'm sorry about the lighting, it's just, these books are shiny. So, oxidation and reduction, one cannot happen without the other. When one happens, the other happens. Okay? That's why it says this, oxidation and reduction are complementary. You're not be able to read that. As an atom is oxidized, another atom is reduced. And when we're talking about oxidation and reduction, what we're talking about is the movement of electrons. If you start to think of bonding as movement of electrons, you're not going to be far off. Okay? So here, down here they show 2Na, well, I don't need to write it, plus Cl2. Actually, you may not be able to read that, so let's just write it out here. 2Na plus Cl2 yields 2NaCl, and then they write the net ionic, okay? Again, that's the same on the front side, but it yields 2 Na pluses and then 2 Cl minuses, right? 2 ions. How did sodium become plus? Okay, how did it become plus? Because chlorine took an electron from it, okay? Now, which is the oxidizer, which is the reducer, which is our oxidizing agent and reducing agent? That's the confusing part, okay? And I'm going to write this right here, oil rig, okay? Oxidation is loss, and we're talking about of electrons. Reduction is gain, again, of electrons. Okay, so sodium, Na to Na plus, it lost an electron, so it was oxidized. Okay? And then chlorine gained an electron, so it was reduced. And you think about reducing the charge is where reduction comes from, so it's getting more negative. The charge is becoming more negative. As for oxidized, I'll get into that in a second, where that comes from. So again, loss. So sodium here was oxidized. It lost an electron. Chlorine was reduced. It gained an electron. Now where the confusion comes in is reducing agent and oxidizing agent. It lost an electron. Sodium lost an electron, so it was oxidized. But what did it do to the other one? It reduced it. So it is the reducing agent. Even though it was the one that's oxidized, therefore it was the agent of reduction for the other one. What did it do to the other one? That's the agent part. It reduced the other one. Here, it was reduced and it oxidized this. So it is the oxidizing agent. And honestly, to me, this is the most confusing part, is that this was oxidized, but that means it's the reducing agent. This was reduced, that means it's the oxidizing agent. Okay? This, honestly, is the simplest way of remembering what's oxidation and what's reduction. Oil rig. Okay? I still remember that from when my professor taught me that in high school. Okay? It works really well if you remember it like that. And again, it's movement of electrons. Did they move away? It was oxidized. Did they come back? Did they move towards it? Did they get on top of it? It's gain of electrons. That's reduction. Okay? And as it goes down here, and it shows you here magnesium and oxygen. And again, this is an oxidation-reduction reaction. Another way to say that, you can't have one without the other. They just call it a redox reaction. Okay? So when I use redox reaction, I mean oxidation and reduction. Both are happening. Can't have one without the other. So here I have two magnesiums and a molecule of oxygen, right? And so that formed two magnesium oxides. Well, okay. Two electrons from the magnesium went to the oxygen. Each oxygen gained 2 electrons. Each magnesium lost 2 electrons. Magnesium lost, so it was oxidized. By what? Oxygen. Oxygen does a lot of oxidizing. Okay? That's where it came from. Okay? Oxygen steals electrons really well. Okay? So that's why we call them oxidizing agents. They act a lot like oxygen. So again, magnesium lost electrons to oxygen. Magnesium is oxidized. It is the reducing agent because it reduced oxygen, because oxygen gained electrons, and therefore oxygen was reduced. Okay? Oxygen gets reduced because it is an oxidizing agent. It causes oxidation in something else. Again, oxidation is loss of electrons, so magnesium got oxidized. Reduction is gain of electrons, so that means oxygen got reduced. Okay, both of them did. Okay? That's the key to this whole chapter, really. As for figuring out, I mean, there's some more complicated parts, don't get me wrong. You get this down, you're going to get a lot of it. Okay? Figuring out how much it was oxidized by or how much it was reduced by, that's where it gets a little bit farther. Okay. So again, here they're showing another one here. And dang, light is shiny. Okay. So I have 2 bromine molecules. Okay. These are 2 Br minuses. Okay. So they each have an extra electron. And 2 chlorines. Okay. Now, that goes to a bromine molecule, this is a chlorine molecule, and 2 chlorine minuses. So what happened here? 1 electron from each bromine negative moved to each chlorine negative, causing them to separate, and these then to combine back. Okay? So what happens is bromine is losing an electron. It goes from a negative to here it's neutral. It has a 0 charge, okay? So when you go from Br minus, so 2 Br minus to Br2, what's happening is the charge on here is 1 minus. The charge on these bromines is 0. It lost electrons. If it lost electrons, what was it? Bromine was oxidized. By what? Chlorine. So chlorine is the oxidizing agent. But chlorine was reduced because it gained electrons. So if chlorine's the oxidizing agent, that means bromine is the reducing agent. It causes reduction. Okay? Moving on. All right. Again, like I say here, the word oxidation refers to reaction with substance combined with oxygen. So here we're taking it to a more general level, not just oxygen, into a specific process that oxygen undergoes. Okay? And it's just like I just said a second ago. They use, this is a weird one, I'm sorry. Light's so bad. Leoger. Leo the lion says ger, or for short Leoger. I prefer oil rig. Leoger is just weird. Okay. So, changes in oxidation number. Okay. So again, oxidation number we learned from those representative elements. Ones in group 1 generally have an oxidation number of 1 plus. In group 2, 2 plus. In group 17 is 1 minus, and so on and so forth. Okay? So it's lost or gained by electrons. So here, looking at this one here, 2K plus Cl2 yields 2K plus 2Cl minus. All right. So, what's happening here? Potassium, and take it out of the reaction one element at a time. So here, I have K. 2K is going to 2K plus, okay? So it means each K is losing 1 electron. Where are they going? They're being stolen by chlorine. So Cl2 is going to 2Cl minus. Each chlorine is going from a neutral charge on K to a 1 plus charge. All right, and then from here it's going from a neutral charge to a 1 minus charge. Okay, so K is oxidized. It lost electrons, so it is the reducing agent. Remember, it's the opposite there. If chlorine gained electrons, so it is reduced, charge got less, and so it is the oxidizing agent. Okay? You got to look for these things, okay? All right. So, and here's where they use some different notation here. They do oxidation number as plus whatever number it is, or so like +3 or -2, and then the ionic charge, it's 3 plus or 2 minus. Okay, it's notation. It's not really that important for what we're trying to do here. It's pretty much the same thing. All right, so we're going to move past that. All right, oxidizing and reducing agents. Again, what we've been talking about. If it was oxidized, it is the reducing agent. Okay? Let me zoom in a little bit. Nope, that's the wrong way. Okay? So K was oxidized, so it is the reducing agent. Chlorine was reduced, so it is the oxidizing agent. Again, it's the opposite. All right? The oxidation number. Okay, so for oxidation, a reactant loses an electron. Okay, the reducing agent is oxidized. Okay, same thing. The oxidation number increases. So its ionic charge increases. Just like for K here. K became here, it needs a 1 plus charge. How do I know that KCl, K is a 1 plus charge? That goes back to ionic compounds. Okay, and this is where it gets difficult because you got to remember that part. This is where it gets a little confusing. So if KCl, okay, that's an ionic compound. What is it? It's K is a +1 oxidation state. All right, and Cl has a -1 oxidation state. Okay? So that's how I know here K was 0. K went from K to K plus. And that's neutral to 1 plus. All right? Cl here was neutral in the molecule. When it's in a diatomic molecule, it is neutral. So, okay, so that went from Cl to Cl minus. Okay, so that's neutral here, again, to a 1 minus charge. All right? You got to go back and you got to remember, okay, these are ionic compounds. They have oxidation numbers. Okay? That's where these numbers come from. If the oxidation number increases, it gets more positive. You can see that. It gets more positive if the oxidation number increases. It gets more negative. Okay, it decreases if it becomes reduced. Okay? So, electronegativity. All right. Let's pause here for a second. Okay, so back here, how to get your advanced math practice tests uploading. So here, redox and electronegativity. Now, it's easy to tell when you have an ionic compound that dissolves. Okay, that you can separate into, where you can get its oxidation numbers. Polyatomic ions, molecules that are covalently bonded are not as easy to tell. Okay? For instance, this reaction here, nitrogen gas plus hydrogen gas yields ammonia. Okay? It's not easy to tell what the charge on nitrogen is, what the charge on hydrogen is, because they don't fully ionize. That being said, unless they are exactly the same atom, there is not an equal pull. Remember back many chapters, I think it was last year actually, I went over it with you really, polar covalent bonds, or covalent bonds in general, it's not an equal sharing. One of the atoms is greedier for the electrons than the other. Okay, that's the one with the higher electronegativity, or electron affinity. That's the same thing. Okay, so the one with the higher electronegativity is going to pull electrons towards it. Okay, so that means it's going to get reduced. So that means lower electronegativity, En, that gives up electrons. Okay, so it's going to be oxidized. Not fully. It's not a full electron movement. Okay, but it's a partial, and so we got to count it. Okay, so, and remember, if you want to remember what this molecule looked like, you have a nitrogen here, and then you have hydrogen, hydrogen, hydrogen. This is 2 electrons, but they're more on the nitrogen than they are the hydrogen. Okay, it's unequal sharing. So, here, nitrogen's electronegativity is greater than hydrogen's electronegativity. How do I know that? One, there's a chart in your book, there's another little chart down here, but as you go left to right, the electronegativity increases, and as you go up, it increases. Now, hydrogen is a little higher than nitrogen. It's like it's one group higher, but nitrogen's so much farther to the right that it is much more electronegative. Okay, so what does that mean? Okay, so if this is true, that means nitrogen is reduced, so it is the oxidizing agent. And if hydrogen, okay, if it lost electrons, or didn't lose it, but gave up some of the electron pull, it is oxidized. And so it is the reducing agent. And just to inform you, hydrogen most of the time, not all the time, is a reducing agent. When you're talking about like this, generally hydrogen is going to be seen as the reducing agent when you're talking about this. So, moving on here, so here we have the first problems I had assigned. Okay. Identify each of the following changes as either oxidation or reduction, and recall that the E negative symbol is a symbol for an electron. Simple enough, right? Let me zoom in here. Eventually I'll edit these properly, but not right now. So, A, I2 plus 2 electrons yields 2I minus. You're going from left to right, what is happening to it? Okay? What's happening to the iodines? They're gaining an electron. Only one. So if it's gaining an electron, that means it's being reduced. I is being reduced. Okay? So if the electron's extra on the left, it means it's being reduced here. Here, B. K goes to K plus plus E. K is dropping, is increasing in charge. Alright? So it's lost electrons. So if it lost electrons, it's been oxidized. Here, iron 2 plus goes to iron 3 plus. It is increasing in oxidation number. And that means, okay, increase in oxidation number means it is being oxidized. Okay, it is losing another electron to get the 3 plus. Here, silver 1 plus plus an electron gives you silver, neutral. Okay, no charge on it. So that means that silver's gaining an electron, so silver is being reduced. That's reduction happening. Okay? Now, identify what is oxidized and what is reduced in the following processes. Okay, so here, bromine goes to bromine 2. These are neutral here. Okay, it's diatomic. That means it's neutral. So it's going from 1 minus to there. So it means bromine is losing electrons. Losing electrons, oxidation. Chlorine's gaining electrons, reduction. Okay? Bromine oxidized, chlorine reduced. Okay? Again, so cesium goes to cesium 3 plus. It's losing electrons, it's being oxidized. Copper 2 plus goes to copper 0, reduced. It's gained electrons. Okay, it went from a positive charge to 0. That means it gained electrons. Zinc plus O2. Both of these are neutral in this instance. Okay? In this instance, though, they are not. Let's look at that. Okay? Right here. 2Zn plus O2 yields 2ZnO. Okay? Here, what's the oxidation states? Zinc oxide. O is always 2 minus, and that means zinc is always 2 plus. And that you couldn't see any of that. Okay? Oxidation state of oxygen is always 2 minus. Okay? And in order for this molecule to be neutral, that has to be a 2 plus. Going back to ionic compounds. If you need the notes for the previous chapters, I do have those PowerPoints. I can put those up if y'all would like. So, going from this, we have zinc goes to zinc 2 plus, and then O goes to O 2 minus. It's neutral to 2 plus. It is neutral to 2 minus. Zinc is oxidized. Zinc lost electrons. Oxygen gained electrons. Oxygen was reduced. Okay? Break that down. Okay, so then we have here sodium plus 2 hydrogen plus, and sodium plus and 2 hydrogens. Sodium goes to 1 plus, lost electrons, oxidized. Hydrogen goes from plus to 0, gained electron, reduced. Alright? Oxidizing agent and reducing agent. Alright, again, it's the opposite of what we kind of think here. So, Fe goes to Fe2 plus. It lost electrons, so it was oxidized. If it was oxidized, it is the reducing agent. Okay, so here iron's the reducing agent. All right, because it lost electrons to this. It was reduced. Silver was reduced because it went from 1 plus to 0. Okay? Iron lost electrons. It was oxidized because it is the reducing agent. It's the agent of reduction. Iron caused silver to reduce. Silver caused iron to oxidize. So silver is the oxidizing agent. When we talk about agent, it's what did it do to the other one. Okay? What did it do to the other one? Not what it is, what did it do to the other one? Alright, and don't worry about the challenge. Let's skip that. Alright, there is a giant chart here about determining oxidation numbers. And if I can get the light to do right. Alright. The oxidation number of an atom of an element is 0. Okay, diatomic molecules, just simple numbers like that, it's 0. Okay. Monatomic ions, their oxidation number is just a charge. That's on it. Alright. Calcium 2 plus is 2 plus. Or plus 2, excuse me. Alright, bromine minus is -1. Alright, so oxidation number of the more electronegative atom in a molecule, or a complex ion that is the same charge it would have if it were an ion. Okay. Nitrogen in NH3. Remember I told you again, I showed up here. It had 3 hydrogens it was pulling from, right? So let's say it pulled that full electron away from hydrogen. So I mean H would be plus, and there'd be 3 of them, right? But then the nitrogen would end up being 3 minus. Okay? Because it's pulling 3 electrons. And if you remember, it's in group 15. Group 15's oxidation numbers are generally 3 minus. Alright? the O in NO, okay? Nitrogen, oxygen, okay? All right. A little different here. All right. The oxidation number of a more electronegative atom in the molecule or a complex ion is the same as the charge it would have if it were an ion. Here, oxygen is more electronegative than nitrogen, so it controls the charge. Okay? So it means oxygen is going to be pulling from nitrogen, and how many is it going to pull? Well, it wants to pull 2. So oxygen is going to pull 2 electrons from that, meaning nitrogen here is going to be 2 plus, okay? Not 3 minus. Okay, covalent molecules is where it gets kind of confusing. You got to look at which is the more electronegative. It's going to pull what it wants, leaving the other one with what's left. Okay, so oxygen wants to pull 2 minus. Well, that's going to take 2 away from nitrogen, leaving it as 2 plus. Simple as that. All right. So the oxidation number of the most electronegative element, fluorine, is always -1 when it is bonded with another element. Always. Simple as that. Oxidation number for oxygen in compounds is always -2, except in peroxides, such as hydrogen peroxides, which it is -1. Okay, so those are your differences here. This is nitrogen dioxide, okay, NO2. Oxygen in there is a -2 charge. Okay, let's look at that one. What's in? So if the O in NO2 equals has a -2 oxidation number. What does the N have? Break it down. There's 1 nitrogen and there's 2 oxygens. So if there's 2 oxygens with a 2 minus charge, that means it has a 4 minus total, right? But this is neutral. Okay? In order for it to be neutral, this plus nitrogen's number has to add up to 0. So that means this is a 4 plus. Nitrogen here is an oxidation number of plus 4. Okay? It gets messy. I understand that. You got to take your time when you're figuring this stuff out. I am going to be lenient with y'all. Y'all do know that. Okay? Peroxides are different. Okay? Just if it says peroxide in it, it's -1. All right? So, and actually, when it's bonded to fluorine, the only element more electronegative than oxygen, the oxygen actually becomes positive. Okay? So, it goes down in terms of electronegativity. Remember, the most electronegative one pulls the electrons away. Oxidation number of hydrogen in almost all compounds is 1, +1. Except in metal hydrides, where it's a -1. Okay? Because, remember, when we learned about ionic compounds, for instance, so there's sodium hydride. Remember, that's the cation. And that's the anion. Oop, again. That's the cation. And that is the anion. Okay? So this is going to be sodium plus, and then the hydrogen's actually going to pull away from the sodium. Okay? It's a hydride. All right? We didn't go over hydrides a lot. I'm not too... I'll go through them as we see. Okay. All right. The oxidation numbers of group 1 and 2 metals and aluminum are positive and equal to their number of valence electrons. Okay? They're like you see. All right. The sum of the oxidation numbers in a neutral compound is 0. Again, like we got here. NO2 is neutral. So the sum of the oxidation numbers has to equal 0. So if I knew this was, oxygen's was 2 minus in here, 2 times 2 minus, that's a total of a 4 negative charge. I have to have 4 plus to cancel that out. Okay? The sum of oxidation numbers in the atoms of a polyatomic ion is equal to the charge of the ion. And there they give the example of sulfate. SO3 2 minus. Okay? Sulfite. I'm sorry. All right, so which is more electronegative? The oxygen is, okay? So that means that there's 1 sulfur and 3 oxygens. Now here, it's not a it's not a peroxide. So I know oxygen is 2 minus. 3 times 2 minus, 6, negative 6 total charge. That means sulfur, in order to add up to this charge, okay, these two numbers, this plus this, has to add up to negative 2. So what plus negative 6 is negative 2? Positive 4. 4 plus. Okay, so sulfur has a 4 plus charge on it. Okay? This comes with practice. I'm going to take my time. We're probably not going to finish this chapter till the end of next week. Okay? It is an important chapter, though. That's why I want to take the time to, and I'm just getting to the lessons with y'all. So I understand. I'm sorry for that. Moving on. Okay. Determining oxidation numbers. So, use the rules we've learned in this table, that you've, I'm sure, memorized by now. Determine oxidation numbers of the bold-faced element in the following formulas and compounds. So they want that particular element. So let's look at, okay, do it like this. A is NaClO4 and it wants chlorine. B is AlPO4 and it wants the P. And then hydrogen, C, excuse me, is HNO2 and it wants the N. Alright. So separate it by its ions first. NaClO4. First of all, ClO4 is perchlorate. Okay? It has a 1 minus charge because sodium has a 1 plus charge. Okay? Damn. Sodium perchlorate. ClO4 was a polyatomic ion. You're going to need to use that chart. I'm pretty sure it's page 221 in the book. I'll get a picture of it later. Alright? Chlorine, O4. Or you can find it online too. So sodium, 1 plus perchlorate, has a 1 minus charge. Now I'm looking for chlorine. I don't need sodium anymore. That's fine. I mean, just ignore it. We can go for this. I want to know the oxidation state on chlorine. Alright, so there's 1 chlorine. We don't know its charge yet. Plus 4 oxygens, which it's not a peroxide, so we know it's 2 minus. That has to add up to this charge, negative 1 charge. So that's 4 times 2 minus, so that's a negative 8. Plus what is negative 1? That's right, plus 7. So that means chlorine's oxidation number is plus 7. Okay? If it's an ionic compound, break it down. You can only do it in pairs like that. Okay? Let's look at AlPO4. Alright. Again, this is aluminum phosphate. Okay? PO4 is a polyatomic ion. It's PO4 3 minus. Aluminum is always there 3 plus. Okay? So then we're looking for P. So here, again, we're going to do the same thing. So P, 1P, and we don't know which charge, that's what we're looking for. Plus 4 oxygens, it's not a peroxide, so it's 2 minus. That has to equal a negative 3 charge. Okay? So, 4 times negative 2 is negative 8 equals negative 3. What plus negative 8 is negative 3? That's right. Positive 5. And that's a 5, I promise. So, phosphorus has a plus 5 oxidation number. Okay? Now here, this is nitrous acid, excuse me. So again, that's H plus and NO2 minus is your polyatomic ion. We're looking for nitrogen, so we don't need this. So N is at some charge, and there's 2 oxygens, and they're always at 2 minus unless it's a peroxide, and that equals, or it's bonded with fluorine, excuse me, and that equals a -1 charge. So what plus 2 times -2 is -4 equals -1. Why, that's right, +3. So nitrogen has a +3 charge, or oxidation number, excuse me. Okay. Number 6, again, same thing. We just did, actually. It's just starting over there, and you already have one thing. Number 7 here. I'll do one at number 6 just to show you here. 6B, astatine peracetate. I forget the exact way to say that one. ASO4 3 minus. Okay, 6B. ASO4 3 minus, and it wants charge of that. So AS is at some charge plus 4 oxygens, peroxide, 2 minus. What is that going to give me? The total charge, 3 negative. Okay, so what plus 4 times 2 minus is -8 equals -3. That's right, +5. So here it has a +5 charge. Okay. Once you get the hang of it, it's just going to take some practice. It's just going to take some practice. So, determine the oxidation number of nitrogen in each of these molecules. Okay? Do it the same way, but these are a little different. Again, ammonia, we've already figured out that one. It was 3 minus because the H was plus. Okay? Because nitrogen is more electronegative than the hydrogen. KCN. Okay? KCN's a little different. 7B. Because that is cyanide. That's potassium cyanide. So that's K plus and Cn negative. Well, that's what we're looking for, right? The nitrogen. So, this is a not an ionic compound. It is covalent. So, which is more electronegative, nitrogen or carbon? Okay, nitrogen is. It's going to pull its electrons. All right. So we have K plus, and then we don't need that, Cn minus. So we have nitrogen has a negative charge here. No, the whole thing is negative. So it's going to pull its electrons. It's actually going to pull what it wants, 3 minus, right? Okay, back on 7B, potassium cyanide. That's K plus and then Cn minus, it's cyanide, that's its charge. So then these two, it's not ionic. Okay, and we don't know which is which. So we look at their electronegativities. And when you look at them, you're going to find that the nitrogen is more electronegative. So it's going to pull its normal charge of electrons. So here, it's going to pull, and it wants to pull 3 minus, because that's what nitrogen's natural oxidation state is. Meaning, if we look back at this, so carbon would actually end up being 2 plus to equal a -1 total charge. Okay? Now remember, when I told you before, we don't usually do group 14 elements as having oxidation numbers. This is part of the reason why. It's because the way they end up working it's not always the same. To put a general rule on it just ends up confusing the situation. So, into H4. Let's look at into H4C, 7C. Into H4. So we have 2 N's, and then we have 4 H's, excuse me. Alright, Now, which is more electronegative, nitrogen or hydrogen? Nitrogen. Okay, so that means it's going to want to pull its actual charges. Okay. Now, the thing is okay. So sorry about that. Okay, so let me just rewrite that. 2 nitrogens at some charge, and then 4 hydrogens at some charge, which normally is a plus. Okay. They have to equal 0 because the whole thing is neutral. So, let's do this. By the way, this is what this element looks like. I mean, molecule looks like. Okay? And the thing is these are each pulling 3 electrons, right? The problem is that ones between here, there's an equal charge, equal electronegativity between the two, so these don't count. Okay? It's only these bonds where we're having the oxidation occurring. Okay, because that's neutral in there. So in reality, normally nitrogen's pulling 3, but the thing is it's pulling equally between 2, so now nitrogen's actually only pulling 2. Because hydrogen is almost always plus. Excuse me, not 2 negative, 2 minus. So 4 minus plus 4 plus equals 0. Okay? Because remember, hydrogen is in most compounds a positive one, and in fact it's a metal hydride. Here, in 2H4, there's no metals here. Those are both nonmetals. So hydrogen is normally plus. Nitrogen there ends up having to be 2 minus in order to add up to 0 for the compound. Okay? Step by step, break it down piece by piece by piece. And you'll get there. Alright, so oxidation numbers in redox reactions. I've already kind of showed this to you a little bit already. And let me zoom out here. Come on. Alright. Already kind of showed this to you already. I'm trying to hit the light just right. So here, shows you various oxidation numbers that things can have. Aluminum's usually plus 3. Barium's usually plus 2. And if you go down further, hydrogen can be 1 plus or 1 minus. Okay? Depends on the situation. Lithium, 1 plus. Iodine, 1 minus. Chlorine, fluorine, or fluoride, either way. Iodine. Alright, lithium, magnesium, usually 2 plus. Oxygen's usually almost always 2 minus, except for peroxides. Potassium, sodium, silver, these are all 1 plus. Strontium, 2 plus. Okay, these are normal oxidation numbers. Having this table handy might not be a bad idea. Remembering this page 688. Page 688 in your books. Alright, or pause this and get a better view of that. Okay? So, in redox reactions, again, you're looking at what changed. Okay? So, let me write this one out. 2K Br plus Cl2 yields 2KCl plus Br2. Now there's 3 elements here, but sometimes nothing changes between a couple of them, okay? So here, what are their oxidation states? Oxidation numbers. So that's plus 1, that's minus 1. Okay? Group 1, group 17. Here, it's diatomic. It's got a charge of 0. Okay? Now look back over here. KCl, group 1, group 17. So that's plus 1 and minus 1. And then Br2 here, that is 0. Okay? So looking at Br goes from a -1 to a 0. -1 to 0 means it lost an electron, meaning it was oxidized. Br was oxidized. Cl went from 0 to -1. It was reduced. Cl was reduced. Now, the weird one is, well, it's not really weird, is potassium. It went from +1 to +1. There was no change. It stayed that. It wasn't oxidized or reduced. Okay, it wasn't involved in that, except that the electron that was stolen kept being stolen from it. Okay? In this reaction, potassium was not oxidized or reduced. Now, before this or after this reaction happens, it may end up being oxidized or reduced, but we're talking about one reaction at a time. Okay, here it wasn't. And you probably can't see that. That is way too light. +1, no change, +1. Okay, and that is a glitter pin. So, okay, that is section 1 of chapter 19. Okay, and next video I will go over section 2.